In previous lecture, we have discussed in very detail the basic equation of general relativity, which was given by Albert Einstein, and you know that very equation is known as Einstein's field equation. In fact, this was the first and foremost, or you can say the basic equation of general relativity. But you know, before Einstein's theory of gravity, there was a well-known Newtonian theory of gravity. Although Einstein came with a completely new idea. In Newtonian gravity, we treat the gravity as a force. But in Einstein's theory of gravity, you know, the cause of gravity was proposed as the curvature of the space-time, not as a force. So according to Einstein, gravity is not a force, but it is just curvature of a space-time. Okay, it is the fabric of a space-time which causes gravity. But surprisingly, you will see that in a particular limiting condition, this Einstein's field equation converts into Newtonian gravity. As you know, when we apply the classical limit condition on the equations of special relativity proposed by Einstein, all equations of special relativity get transformed into Newtonian theory or Newtonian mechanics under the classical limit condition. In the same way, we will see here there is a limiting condition which is called non-relativistic limiting condition or Newtonian limit, under which Einstein's field equation will agree with the Newtonian theory of gravity. So this is a very interesting fact that Einstein's field equation supports Newtonian theory but under some limiting condition. So what are those conditions in which Einstein's field equation will converted into Newtonian theory of gravity? We will learn, and how we can mathematically prove it. Actually, for mathematical proof, you know, you have also seen in previous lecture that Poisson's equation in presence of matter is a natural outcome of Newtonian gravity. So if you are able to derive Poisson's equation under a proper limiting condition from Einstein's field equation, then you can easily say that Einstein's field equation gives Newtonian theory of gravity under the non-relativistic condition or Newtonian limit. So this is the subject matter which we are going to discuss in this very interesting lecture. So this is a very informative, very important and very useful lecture for you. So be serious, watch the video seriously with your notepad and with your pen, and write down each and everything, and then you will see that each step of my lecture will be clear to you. Okay, so just I am starting what you have learned in my previous video, that is the Einstein's field equations. You know, the Einstein's field equation in general relativity is written like this. This is G mu nu, which is equivalent to R mu nu minus 1 over G mu nu times R, equal to this much. Okay, if you want to write this equation in natural unit, you know, when we take natural unit, we simply take c equal to 1, which is speed of light. Okay, so if you will take c equal to 1, then this equation will be written in natural units. So this second equation has been written in natural units, which is also Einstein's field equation. And for more simplification, we use relativistic units. And in my previous video I have already discussed this relativistic units, and you know, in relativistic unit both of these universal constants c and g are taken 1. So if you will take this g also equal to 1, then this equation which is Einstein's field equation is in relativistic unit. Okay. Our aim in this lecture is what? Our aim is to show that this field equation which I have mentioned in this equation 1 agrees with Newtonian gravity but under some particular condition, and those conditions are actually called Newtonian limit. Okay. So I have mentioned here the meaning of each and every term, although you know because you have already studied this field equation in my previous video. But for clarification, I am just repeating the things that you know. This R mu nu, this is the well-known Ricci curvature tensor, and this capital R, which is called Ricci scalar curvature. G mu nu, this is a well-known quantity of tensor analysis. This is called metric tensor or fundamental tensor. T mu nu, you have already discussed in my previous video in very detail. This is energy momentum tensor. G is Newton's gravitational constant or universal gravitational constant, and c is speed of light in free space. Okay. Actually, these equations you can see connect the geometry of the space with the distribution of matter and energy. How? Because in LHS you can see the value of this R mu nu and G mu nu depends on the geometry of a space. So LHS of this equation refers the geometry of a space, and in RHS there is T mu nu, which is energy momentum tensor. This depends on the distribution of matter and energy. So we simply say that Einstein's equation connects the geometry of a space-time with the distribution of matter and energy. Okay. Now, what is our aim in this lecture? As I have told you that our aim is to show that this field equation is transformed into Newtonian theory of gravity. It explains the Newtonian gravity under some proper limits, and those limits are called Newtonian limit. Okay. When you say Newtonian limit, what does it mean? In fact, in case of Newtonian limit, you must have to take weak gravitational field. Okay. And when we take our gravitational field is weak, then space-time is almost flat. You can say our space-time will be in fact M.Sc space-time. Okay. Although Einstein has talked about the curved space-time, but since we are going to transform Einstein's field equation into Newtonian theory of gravity, so we must take under account that we have to take a weak gravitational field so that the space-time will be almost flat. Okay. Again, Newtonian mechanics always holds at low speed. So definitely motion should be slow. When you say motion should be slow, what does it mean? It means if v is the speed of our particle or any object or system, then this v must be much smaller than c. Okay. This is called in fact classical limit. And the fields must be time independent. It means you have to take the static field. So when we will take a static weak gravitational field and the system will be in slow motion, then under these conditions you will see that the theory of general relativity will reduce to Newtonian theory of gravity. Okay. So you can say that Newtonian gravity is not incorrect, never say that Newtonian theory of gravity is incorrect. It is limited. It holds in case of weak and static gravitational field when the motion is slow. Okay. So under these conditions, what will be the form of Einstein's equation and how it will agree and how we can derive Poisson's equation from it? Now we will see. So first of all, we will talk about what will be the metric in this weak field limit. Okay. In fact, when you talk about weak field, then as I have told you that the space time will be just flat, almost flat. It means not completely flat, but almost Minkowski space time. So there will be a little perturbation in Minkowski space time when we talk about the weak field limit. Okay. So for weak fields, we can choose a coordinate system in which is almost Euclidean, or you can say that we write the space-time metric as a small perturbation of the flat Minkowski metric. Okay. So this G mu nu, which actually represents the geometry of or the curvature of the space-time, this fundamental tensor, this can be written as eta mu nu plus h mu nu. Actually here, this eta mu nu, this is metric for Euclidean space, and this represents the completely flat metric or flat space time. But there will be a little perturbation, because you can't take completely flat space time, because in that condition you are not talking about general relativity. So this h mu nu is the small perturbation which makes the space time slightly curved. Okay. So definitely this h mu nu, which is perturbation term, that should be much smaller, very small. So you can say that the modulus of this h mu nu should be much smaller than 1. Okay. Now, when you have studied in my lectures on fundamental tensor, that when we talk about weak fields, then the metric differ very slightly from the metric of spatial relativity. It means the metric of it means the flat space time. And in that condition, you have seen earlier that this G11, G22 and G33, all these three are almost equal to 1. Okay. And what will be G44? Actually, in Newtonian gravity, the gravitational potential phi affects the time interval, and so the G44 component of the fundamental tensor is related to this phi. And how these two are related? Actually, this G44 is given as minus 1 plus 2 pi over c square. Okay. You must remember this result. Okay. And if you will write this equation in natural unit, then you have to take c equal to 1. So in natural unit, you can write this G44 is equal to minus 1 plus 2 pi. And also you know this G mu nu is 0 for all those G for which mu and nu are different. Okay. When mu and nu are different, for example, if you talk about G12, G21, G13, okay, all these are equal to 0. Okay. Now, now you should know that when we talk about weak static field means time independent field and whose strength is very weak. Then among the four components of velocity, the three Cartesian components are zero. You know, the three Cartesian components of velocity are given as dx1 by ds, dx2 by ds, and dx3 by ds. All these three are zero, okay, yeah, or the order of zero when we talk about weak static field. But its fourth component, which is related to time, that is of the order of 1. Okay. So in this condition, first of all, we will evaluate the value, the four component of this energy momentum tensor. In general, you know, the energy momentum tensor is defined like this. This is its basic definition. You have learned in previous lecture. So if you sum up all the components of the velocity, you can see the first three terms containing dx1 by dx, dx2 by ds, and dx3 by ds, those will be zero. Only the fourth term will be in this expression, which is non-zero, and therefore by using equation 4 we can easily say that this T mu nu will be simply equal to rho times dx4 by ds times dx4 by ds. Okay, because in Newtonian limit you can see this equation 4 that all other components are 0. But dx4 by ds, you can see here this is almost 1, so this is rho times 1 times 1. Therefore this energy momentum tensor is simply equal to what? This is simply equal to the material density. Okay, and you also know that the value of this energy momentum tensor, either it is covariant energy momentum tensor or contravariant or mixed, all are same, and therefore in general we can say that this T44 is equal to rho. So now we denote it by the symbol T. Okay, so in this way we have evaluated the value of energy momentum tensor. Okay, only the fourth component is non-zero. Now let us start with Einstein's field equation. You have seen, I have mentioned earlier in equation 1a3, this is your Einstein's field equation in relativistic unit. Okay, now to get our final result, you have to remember that we must take the product of this equation by this fundamental tensor G mu nu. So taking product of this equation by this fundamental tensor G mu nu, our result will be G mu nu times R mu nu minus this much equal to this much. But you know, the product of G mu nu times R mu nu, this is simply equal to Ricci scalar curvature, and this product, what is this? G mu nu times this G mu nu. I have mentioned this fact previously in dealing the problem of Einstein's field equation, that this product is equal to 4. So instead of this I have written here 4, you can see, and again the product of G mu nu times T mu nu, you know, this is equal to simply T. This superscript and subscript, you can say that they cancel out. So this is R minus 2R, which is equal to minus R, and that is equal to 8 by T, and therefore you can say that this Ricci curvature scalar is equal to minus 8 by T. Okay, now we will use this result defined in equation 6, that is R equal to minus 8 by T, and this equation 5, where we have evaluated the value of energy momentum tensor T44, which is equal to rho. In equation 1a3, which I have mentioned here for the fourth component. Okay, because our final aim is to evaluate R44. We will see later. So instead of R mu nu, now we write R44. Okay, it means you have to replace mu by 4 and nu by 4, and then this equation will transform like this. Okay, and therefore R44 will be equal to this much plus this much. Okay, you can see R44 is 8 pi rho. Why rho? Because you know this T44 you have seen in equation 5 that this is equal to rho, and this is 1 by 2 G44 times 8 pi T. But G44 you have seen this is equal to 1, so this is 8 pi rho minus 1 by 2 8 pi rho, so this is simply 4 pi rho. So R44 is equal to 4 pi rho. Now we will evaluate this R44. Okay, how we can evaluate R44? For evaluating this R44, we have to start from the general expression of Ricci tensor, and I have provided a separate video on Ricci tensor. Why I have provided? Now you can understand, because the use of Einstein tensor, Ricci tensor is always found in a study of general relativity. So I have discussed these things in my previous videos, and you have seen that this Ricci tensor R mu nu is defined like this. You can see here. See this expression. All these gamma are, you know, these are affine connection, or you can say these are Christoffel symbols. Okay? So if your aim is to find the value of R44, then in this expression, everywhere in each term, mu and nu both will be replaced by 4, and other subscript or superscript will remain at each. So this equation will transform like this: R44 equal to del del x4 operated on this affine connection or the Christoffel symbol minus 1 del del x lambda operated on this Christoffel symbol plus this much plus this much. Now see the last two terms. The last two term contains the product of two affine connections. So they are actually the quadratic terms. But for linearize the equation, we will consider the first order approximation. So in first order approximation, these last two quadratic terms are neglected. Okay. So in first order approximation, we will write that R44 is equal to the first two terms in RHS. Okay. So I have written here that you can see R44 is equal to this much. Okay. Now what will be the value of this first term? What will be the value of this second term? Now we will analyze it. You know that this G mu nu, it is not a function of time if the field is static. In a static field, this metric tensor is not a function of time. And when you say that it is not a function of time, it means its derivative with respect to the time coordinate. Here x4 is what? X4 is time coordinate. That will be equal to 0. And if it is 0, then first term in RHS of equation 1, where you have written the partial derivative of this affine connection with respect to the fourth coordinate x4, that will be 0, because you know this Christoffel symbol is defined in terms of this g mu nu, and therefore this term will vanish, and if it is 0, then R44 will be simply equal to this much, that is minus del x lambda operated on this gamma lambda 44. Okay. But if you talk about the value of this R44 when lambda is also 4, then this will be 0. It means del x4 operated on this will be equal to 0. Why? Because you know that this del g mu nu by del x4 is 0 for all values of mu and nu, for all values. And this g4 alpha is also 0 for alpha equal to 1, 2, 3. Okay. So in these conditions, you can evaluate the value of this R44 by the use of this equation 9. Okay. Fourth component is 0, and for non-zero component you should take only the value of affine connection up to lambda equal to 1, 2, 3, not 4. Okay. So I have replaced the symbol lambda by alpha, and alpha should be taken only 1, 2 and 3, not 4, because for fourth component it will be 0. Okay. So R44 then will be equal to minus del x alpha operated on this affine connection. Okay. But this del x lambda this much then will be equal to this. Why? Because you know that this R44 we have already obtained here. R44 is equal to 4 pi rho. So instead of this R44, now we will write this much. Okay. I have substituted minus sign in RHS. Okay. Now let us evaluate the value of this gamma 44 when alpha runs from 1 to 3. You know, in the defining equation of this gamma, there is 1 over 2 del g mu nu by del x nu plus other terms. All other terms will be 0 except this del g44 by del x lambda. So simply you can say that this affine connection is equal to this much. Now we will substitute this value of affine connection in equation 11 in LHS. So instead of this gamma, I have written here this much. You can see. And you know here alpha is the repeating index. So in accordance with Einstein summation convention, this term does not represent a single term, but it is a sum of 3 terms for the 3 value of alpha from 1 to 3. So we can write using the Einstein summation convention that this is equal to summation alpha 1 to 3 del 2 g44 by del x alpha. Okay. Del x alpha. Del x 2 alpha del x square. Okay. And this factor 2 has been multiplied here, so this is minus 8 pi rho. But you know that summation del 2 by del x square, what is this? This is actually del square Laplacian operator, okay, in Cartesian coordinate. So here instead of this operator del 2 by del x, summation del 2 by del del x2 alpha, you can write the Laplacian operator del square. So Laplacian operated on g44 is equal to this much. But you have seen that this G44 is equal to 1 plus 2 phi in natural unit. Okay, minus 1 plus 2 pi. So here I have written minus sign. You can see minus minus in both sides will cancel, and when you will operate this del square on 1 is a constant, so that will be 0. So that will be simply 2 times of del square phi, and when you will divide this 8 pi rho by 2, then your equation will be del square phi equal to 4 pi rho. Can you say what is this equation? This equation you can easily say that is in fact the Poisson equation in a relativistic unit. If you will write Poisson equation in general, then this is written as del square phi is equal to 4 pi gc square times rho. Okay, times rho. But in relativistic unit we take g equal to 1, c equal to 1. So this is Poisson equation. So you can see how we have derived this Poisson equation starting from Einstein's field equation. Poisson equation is just the outcome of Newtonian theory of gravity. Okay, it is a classical equation, and we have derived it from Einstein's field equation. But how? You have seen this equation has been derived when we have imposed the Newtonian limit conditions. Then the outcome is this Poisson equation. So you can say that relativistic general theory of gravitation corresponds to Newton theory of gravitation in the presence of matter in a non-relativistic unit limit, or you can say Newtonian limit of a weak static gravitational field. Okay. Just as a summary, you can say that Einstein's gravity is transformed into Newtonian gravity when the gravitational field is weak and slow motion dominates. Okay, and Poisson's equation arises naturally from the 4 component of the Einstein field equation in this limit. Okay, so I think you have clearly understand when the Einstein's theory of gravity will agree with Newtonian theory of gravity. What are those conditions and how mathematically we can prove it? For mathematical proof, you have to start from Einstein field equation and impose the Newtonian limit on those equations, and then you obtain the Poisson equation, which is an outcome of Newtonian theory of gravity. So in this way, we have clearly explained that Newtonian theory of gravity is just a limiting case of Einstein's general relativity. So never say that Newtonian theory of gravity is wrong. It is incorrect. It is limited. It will hold, but it will hold only when you talk about weak gravitational field, a static gravitational field, and slow motion. Okay. Thank you very much.